if I have point C over here, or if I choose a condition over here, which is known as point C, right? So what will happen is point C will be a dot, right? So condition point C, right, will be a dot. You can't get a circle, okay? Because stress A and B are at the same point. Okay, right. But it's still within the operating boundary, most important. Okay. So we have not figured out how this region works yet. We have not figured out how this region works yet. Okay. We don't know how this region works yet. Right. So now I'm going to sketch how that region works. Okay. So I'm going to, yeah, I think I'm going to, yeah, wait. I want to magnify so you can see better. Some of you ask me, why am I teaching this? Because this will affect the analysis later on when we do compound loading condition, okay? And in a PO exam, this is under advanced strength of material, okay? But I'm not bothered whether it's this advanced or not. More important thing is, as a designer, we have to know, okay? Then, again, I'm going to sketch Mole circle, okay? So this is our normal stress. Then this is our shearing stress. I don't need to be so. All right. So your shearing stress, clockwise, anti-clockwise. I'm still going to draw the operating space. Okay. Yeah. Without this, we can't design anything that need to be certified. Okay. So I'm hopeful that you guys will be designing structures that need to be certified. Important structures or critical components. Okay. Right. So I'm going to see how the yellow region works. So the yellow region that I shaded is very interesting. Okay. It has tensile and compression. I repeat again, it has tensile and compression. Okay. So let's pick a point. Okay, let's pick a point. So let's say we have a condition over here. Okay, that is our condition A, B, C, D. I'll consider. Okay. So at this condition, what is going on is we have the stress in B in tensile, the stress for A is in compression. You can see that, right? Right. So okay. So what it means, so stress A is in tensile. Sorry, stress B is in tensile. Okay, so stress B is in tensile. Again, this point is our stress U. Okay. Sorry. So this point is stress U. This point over here is your minus stress U. This point over here is stress U divided by 2. Over here is minus stress U divided by 2. And point and stress A is in compression now. Right? It's in compression. So now if I were to draw the circle, the Mole circle, it will be a full circle. Okay. So if we were to reach another condition, okay, if we were to reach point E, right? So this is point E, condition, oh, sorry, condition E, not point E. I do apologize. Okay. So this is for, this circle is for condition D. Oh, I forgot how I label. Okay. So I should have labeled D. Okay. So this is D. stress B, and this is D, stress A. And I'm going to pick another point E, right? So for E, what you realize that stress A is over here. And again, over here is E for stress B. Okay, so I use a different color. I draw the circle. Okay, so this is for condition E. Okay, so that's how the circle works. So what you realize, okay, so this is, so if we were to look at the quadrant, right, so this is our first, so this is our first, second, third, and fourth, right? So the top graph or the top most circle or the above row most circle is more suited to the first and third quadrant. Okay, so the first and third quadrant, what changes there is the circle changes in size, right? You can see I just did a few examples of how the structure or how the circle will vary when we put different condition at point A, B, and C, or it can even be a point. You can see over there. But when it is in the second and third and fourth quadrant, right? Second and fourth quadrant, you realize that the diameter did not change. It has been maxed out, right? But it shifts, right? It shifts depending on where we are. Okay. So now, based on this concept, bear with me, okay? When we apply it, it's really, really easy. Okay, it's really, really easy, right? So based on what we have, okay, when we were to find principal stress, or why we find the principal stress, okay? So we have to find the principal stress. Okay. I.e., we have to find stress A and stress B. And from this, right, stress A and stress B, we are going to compare with stress U. Okay. We have to compare with stress U. Okay. Farus, I see your message, but I have to proceed. Maybe you can watch the video. Okay. So stress U is equal to stress A minus stress B. Okay. So this is a criteria. Why this is one of the criteria? So because this is a material property. Over here is calculated stresses. Okay. Over there is a calculated stresses. Okay. And then when we, after we have this criteria over here, we have another condition, right? And when we write out this expression over here, right, it has to be also, or before I write that, right? So we know that I'm going to call stress A. So let stress A equal to stress max. Okay. Stress B equal to stress mean. Right? Or you can flip. Okay. Stress B can be mean and the other max. Okay. So we know that stress U is equal to stress max minus stress mean. And this, with this case, we know that this is also equal to our tau max. So therefore, right? Or tau or not, this is, sorry, this is not equal to tau max. Come on. So tau max is equal to stress U divided by 2, which is equal to stress max minus by stress mean divided by 2. So again, this is material property. This is what? This is calculated. Okay. So we are going to do an example now. Okay. And this example has a lot of analysis. So my advice to you, if you can, okay, listen. Okay. Don't worry about copying. Okay. Listen. Okay. Or if you have to copy, do so. Okay. Right. So this is example number. Before I go on, anyone, any question? Or Fairuz, what's your question? Since I'm asking questions now. Fairuz, are you still there? Or you can't speak on your mic? Okay, he's not responding. Okay. Yes.
Any point from the highlight, like a space, is supposed to be in the green, like a square box.
Say it again.
Any point from the highlight, you highlight space left side, and then it's supposed to be the whole circle supposed to be the on the green box.
Did I do something wrong? Which one?
No, I mean just confirm it. Just any point from the left hand side, you draw the space, highlighted space, right?
Mm.
And any point from the like ABC, any point from the there, and then the whole circle supposed to be the in the inside of the green square box, right?
Yes. Always.
Oh, okay.
It cannot go out.
Okay, get it. Thank you.
So point F, okay. So if you look at point F, right? So point F is something inside, somewhere inside. Okay. So there's a question by Chin Tan. So this is point F. Oh, I know what he's trying to say. So he's right, okay? So at anywhere on point F, okay, the circle will be smaller, okay? The circle will be smaller. But what I'm highlighting down here, okay, so Sinta say if it's point F, what will happen? What I'm highlighting down here is the line, is the boundary, sorry. So if I were to draw at condition F, okay, so both will be compression. Okay, so both will be compression. This is just a sketch, okay? He's right. Okay, so one will be here. So this is condition F. Okay, this is just a sketch. Okay, this is condition F. Sintan, what I'm trying to highlight down here is more, okay, what I'm trying to emphasize is on the boundary. Okay, well caught. Okay, so you see down here where I put all the points are on the boundary, right? On the boundary, where the slope is, where this condition, the yellow condition, the circle will always be big circle. Over here, right? If you can see over here, on the boundary, the circle is changing in diameter. Does that make sense to you now, Sintan? Okay, I'm highlighting that what is going on the boundary. Okay, on the boundary means on all these lines. These are all the boundaries. These are all the boundaries. Sintan, does that make sense?
Yeah, absolutely.
Okay, it's on the boundary I'm highlighting. Okay, so because within inside, no problem. Everyone is happy, hunky-dory. It's on the boundary, how it behaves that is important. Okay, right.
I had a quick question, Eugene.
Yes.
If we were to pick a point that's outside of the that's outside of Tresca's boundary, does that mean that the circle would also be outside of the rectangular boundary as well?
Yes, it will be outside.
But would that also mean that the stress that we chose is more than what the material can withstand?
Yes, I mean does not mean failure will occur. For ductile material, it will plastically deform.
Oh, I see. Thank you.
Right. for brittle material, it will fail. Okay. Farus, you say you missed the first 5 minutes of class. Can you briefly explain where we would encounter this shape? When you say